For the first homework problem, we're asked to watch a YouTube video about the Copenhagen telephone exchange, and then to use the queuing theory calculator. I pulled up the website on the right-hand side and kind of replicate the results that this Danish engineer came up with in order to figure out how many trunk lines they should use for the telephone lines. So first thing I'm going to do is play part of the video where they discuss the Copenhagen telephone exchange, and then tell you how you can pull out that information to input into your queuing model. And then just to keep in mind, we're asked to look at our queuing theory outputs when you have 7 trunk lines and then when you have 6 trunk lines.
It's important. It's a study of early phone systems. It began in 1909 at the Copenhagen Telephone Company, where an engineer there, Agner Erling, asked the question, how many trunk or main telephone lines are needed to adequately service a town? Now, you could put in just one. There would be huge delays because of blocked calls. You could install one for each phone. It's expensive and wasteful since not everyone calls at once. The telephone company needed a trade-off between these two extremes. To see what Erling did, let's look at a town where there's an average of 2 calls an hour. You'd think 2 trunk lines would do, but Erling showed that although the average rate is 2 an hour, the calls will bunch up. A lot of times it will be only 2 calls, but also sometimes none, or 3 or 4 or 5 will occur. He showed that given the average number of calls and their average length, one can estimate the number of trunk lines needed. To make the calculation simple, I've assumed that Danes like to talk a long time, 1 hour on the average. Erling showed that for only 1% of the people to have a blocked call, you need to install 7 trunk lines. What has this to do?
Okay, so I'm just going to go back a little bit. Okay, so here's the important information we need. We're given that the average call duration is 1 hour, so you can say like, oh, there's one customer, a customer spends an hour talking on the phone, and we're also told that the average arrival rate is 2 per hour. So you have 2 customers trying to call during 1 hour, and then we're given that the number of trunk lines is 7. So now I'm going to input this information into our queuing model. So I'm going to go over to our website, and then here we're going to check the first option, MMC. So there's 1 queue, and then we have C servers. So I'm going to select the model. Now I'm going to scroll down. Okay. So the number of servers is the same as our number of trunk lines. So in this first example, because we're asked to show how Erling came up with this number of ideal trunk lines to use, we're going to input 7, and then here we have our arrival and service rates. Okay, so first for our arrival rate, we're told that there are 2 calls per hour. And then we're also told for the service rate that each person spends about an hour on the phone. So I'll put this as 1. Okay. And then once again, we are told that we have 7 trunk lines, that 2 customers call every hour, so that's our arrival rate here, and that the customer spends 1 hour on the phone, right? So then you can serve an average of 1 customer per hour. So then we're going to go to calculate. So I'm going to change this into minutes, just so it's a little bit easier to understand. So this tells us that at a given moment there's about 2 customers usually that are making phone calls. Less than 1 customer is spending time waiting. And then they spend an average of 60 minutes on the phone. And they don't spend that much time waiting in line, so waiting to be able to make a call. Right, and if we look down here, this is the time that they're spending in the queue, so the amount of time that they spend waiting. So if you're looking at this, the probability of the time that they spend in the queue, so because we have 0 here, this means the probability that customer doesn't have to wait at all, it's 0.9952. So that's 99 over 99%. So remember that Professor Lu gives us the hint that if you take this number and subtract it from 1, you'll get the blocking probability. So 1 minus 0.9952 is less than 1%. So this is how you would do homework problem 1, part 1. So again, here I just entered in the number of servers, 7. Our arrival rate was 2 per hour because we're given this information that the average arrival rate is 2 per hour. And our services per hour is 1 because we're told that each customer spends about 1 hour on the phone. So now for the second part of homework problem 1, we're asked to figure out the blocking probability if we're only using 6 trunk lines. So again, the blocking probability was found by subtracting this number from 1. So what we're going to do is just keep this information the same, so don't change what kind of model we're going to use. Again, we still know that there's about 2 customers per hour and that they spend 1 hour on the phone. The only thing we're going to change for part 2 of homework problem 1 is the number of servers. So I'm going to change this to 6. Go to calculate. So again, I set this to be in minutes, so it's telling us information. There's about 2 people trying to make phone calls. They spend about an hour on the phone. And then here, if you notice, they spend about 27 minutes waiting in line to get access to a phone call. And if you go here, you'll see that the probability of the time that they spend no time waiting is actually 98.2, right? So if you did 1 minus 90.982, that's actually greater than 1%. So again, here for homework problem 1, part 2, all I did was change the values so that the number of servers is 6.